So I just handed out a calendar that tells you what we're doing, or it's a calendar of kind of assignments and things that you should know leading up to the end of the semester and the final. So the homeworks for chapters 8 and 9 are going to be, and I believe that I checked the time on all of them, is midnight on the day that it's listed on the calendar. Okay, so Sundays and Wednesdays, okay, at midnight. The last day of class will be the exam that's on chapters 8 and 9. And I will have them graded, and you can pick them up on the study day. I'll have them in my office. And then our final exam is an early morning one on the 13th, so that's the Monday of final exams week. Just a heads up, you can always do the Mind Tap late for, a late penalty. But because of final exam grading, you will not be able to do any homework after the time of the final exam, okay? And the whole point is the homework is the best way to learn the material and prepare for the assessment, which is the final exam. Particularly with the chapter 8 and 9 material, we are getting into the course content that is calculation heavy, okay? But hopefully you will think of everything as we're just doing one type of calculation. We are doing a unit conversion, okay? Percent composition, there's a few little additional things to that, but when we get to stoichiometry and chemical reactions, any of the math that we have to do is just, I'm trying to get rid of the word just from my vocabulary, but try to look at everything as what do I have, what type of quantity do I have, and what unit do I need to get to? So if I'm trying to figure out how many grams of product I can have, and I'm starting with grams of reactant, you'll have to go through several steps, right? You'll have to convert, like you did in the limiting reactants lab. So we're going to be redoing those kind of calculations where we have to go from grams to moles, and then use the mole to mole conversion from the chemical equation, and then go back from moles to grams. Okay, so we're really doing kind of coming full circle and going back to where we started, which was with converting between different types of units. Okay. All right. But before so does anybody have any questions about the end of the semester schedule? And just to note that the final exam is going to be all multiple choice. And the reason for that is that it helps me with grading it and dividing up the questions by topic and calculating your percentage on the exam 1 material so that I can improve your exam 1 grade if need be, okay? So, and things like that. All right. So if there are no questions about the end of semester schedule, okay, I want to just say a few quick things about the end of chapter 7, okay? So this will not be on the exam number 4, but there may be one question about bond rotations and isomers on the final, okay? So, all right. So if we're talking about, pi bonding, okay? So we've got our sigma bonds where we have our hybrid orbital overlap, okay? And pi bonding is when we have overlap between just your regular p orbitals that are kind of above and below the bond, okay? So there's two different types of things there, okay? And so if we're looking at this molecule like benzene, where we have kind of alternating single and double bonds, okay? But you can think about our Lewis structures and resonance, and hopefully you'll realize that, you know, we also can have a version where these three bonds are double bonds, okay, and these ones would be single, okay? So we've got those kind of two resonance structures. So when we look at the molecule as a whole, okay, what we have is we have sigma bonding between all of the carbons, okay, as shown here, and then the electrons in the pi bonds, the second bond of the double bonds, are really going to spread themselves out over all the carbons because we have those two resonance structures and they're equivalent, and so each is equally likely. So what you get when you have something like benzene, okay, when you have a ring that has alternating single and double bonds, is you have regions of electron density, so where the electrons may be at any point in time in this kind of zone above the ring and one below the ring, okay? And what that means is if I were to have, let's see if it will let me do this. Oops. Copy. Paste. Yeah, it's not gonna look great. Let me crop it so that. There we go. Okay, now it's not working at all. All right. Let's just give up, and I'll draw it. All right, so if we have one of these molecules stacked over one another, I am a terrible artist. So just imagine we have another one stacked here, and it has this similar kind of cloud of electrons, okay? What we're going to get, okay, is you're going to get a force that's kind of attracting those molecules to one another, okay, because of something you'll learn about if you take Gen Chem 2, which is called dispersion interactions, where the electrons induce dipoles in one another, okay, and then that makes these things attracted to each other, okay. So when you have this type of pi bonding arrangement, you can get attraction between molecules that are similar. And as I mentioned in the pi bonding video that I posted before the exam, this is a phenomenon that plays an important role in the stability of DNA, and so it's worth mentioning and knowing about. Okay. So we're still going to be thinking about sigma and pi bonds, but now we're going to think about the impact they have on whether we can do what's called rotate around a bond. Okay, so if you look at these, these arrows here get rid of that. There we go. All right, so we've got a single bond here, okay, and there are 3 hydrogens attached to each of those carbons, okay? And so when we talk about rotating around a bond, you can think of it as if I have, 2 things let's just think about my hands, okay, as the 2 things attached to the end of the stick. I can rotate, my hands, so if you're looking at my ring, it can either be down, it can be up, it can be back, okay, and I can rotate around that very easily. Okay, so when we talk about bond rotation, let's just imagine, okay, that this atom right here is a different element. Okay, let's say it's like a bromine or something, right? So when we talk about bond rotation about a single bond, if I'm looking here and I've got my 3 things that are attached, when I say that I can rotate, okay, it means that, in space, these things can change position. So if I rotated so that, oops, and I'll rotate this one down, what would happen is this would be a hydrogen, the bromine would be here, the hydrogen would be here. If I'm rotating this one kind of in the other direction, I could get the bromine up here. Okay, so that's what I mean with bond rotation. I mean the things that are attached at the end of a stick can spin around. Okay? All right, so that's what we get, when we have a single sigma bond. Okay, so we can rotate around this. Now, when we look at, and that's because if we look at this region right here, okay, if we're spinning, okay, if we spin these things around, okay, that orbital overlap can still happen, right? Okay, and nothing changes. So if those 2 things are overlapping, I can rotate around them and they still overlap. Okay, I'm not breaking any of that overlap. Now let's look at if I have 2 separate things, and which is the pi bond. Okay, so now I have 2 separate things, and in order to rotate around them, okay, I would have to do what's called breaking conjugation. I would have to break some of that electron density and then reform it, okay? So in this case, okay, so here's my pi bonds. We cannot rotate around a pi bond, because to do so, you'd have to kind of create a state where the electrons are likely to be nowhere, okay? And we know the electrons exist and they have to be somewhere, okay? So that's kind of why you can't, okay? So the simple rules to follow in terms of how your molecules can move with respect to the atoms that are in the molecule. Okay, so this is let's make it very clear that this is what we call intramolecular. So that means intra means inside. Okay, so that and this implies inside, a molecule, it's a single molecule itself. So what that means is, the position of atoms within one molecule with respect to each other, okay? All right, so the take-home message is that rotation can happen around single bonds and cannot happen around double bonds, okay? All right, so this is just, showing you with a model, okay? We can, if this part of the molecule rotates, okay, the bond, that overlap is going to be unaffected. Okay. But pi bonds, again, we represent as overlaps between these things over here, the p orbitals. Okay? And so if I rotate this one, okay, this orbital is going to move away from the one that it's overlapping with. Okay, so when I say breaking that conjugation or breaking that overlap between the pi bonds, okay, that's what I mean. If I'm moving this, then I can't overlap with that one, and I can only overlap with another one when I kind of finish a rotation that moves me back into position. Okay, so that's the difference again. Okay, so what impact does this have in terms of molecules? It's in terms of as we get to larger molecules with more atoms, okay, and especially in organic and biochemistry, okay, we have differences, okay, in molecules that can happen easily with temperature when we can rotate about something, or differences that are going to require some type of chemical reaction to occur, okay? So we have things called conformers, okay, or conformations, okay? And those are just different temporary shapes of the same molecule, okay? So they're the same molecule, and you get these when you can rotate around single bonds, okay? So rotation about single bonds. So if we look at the bottom left side of the screen, okay, we have two molecules here, and they've got two carbons, okay? So like in the previous example, we have two carbons attached, and each carbon they're attached by a bond, and each carbon has three things attached to it, two of which are hydrogens, and one of which is what we call a methyl group, a CH3 group, okay? And so this is the thing that's different that's going to allow us to see whether the molecule has changed, right? And again, because this is a single bond, okay, I can rotate around it, so it's like I have one thing at the end that I'm just spinning, okay? And so when I do that, okay, the position of this CH3 right here changes, okay? And that can just happen, with temperature as things move, that can spin around, okay? Okay, so now, okay, let's look at if we have molecules with the same chemical formula, okay, but a different structure, okay? So in this case, okay, we've got 3 carbons attached and 1 oxygen, and then 8 hydrogens, okay? So we could have these 3 different molecules, okay? Okay. So everything is still connected with single bonds, okay? So we can rotate about all these bonds, okay? But in this case, the position of, this is called a hydroxyl group, okay? So similar naming to the hydroxide ion, okay? But in this case, okay, we can make a version of the molecule where the oxygen is interior and it's not attached to a hydrogen, okay? So these different molecules are what we call isomers, okay? All right, so these are different ways of arranging the same set of atoms, okay? And I'm going to say different ways of connecting. So isomers are different from resonance structures, okay? Resonance structures, all your connections are or who is connected to who in terms of being an atom or an element is the same, but maybe the number of bonds or number of lone pairs differs, okay? With isomers, okay, what you have is who is connected to who is different, okay? So in this case, again, you can see, my middle carbon, it can have a hydrogen attached, it can have an OH attached, or it can have, you know, 2 hydrogens and be covalently bonded to an oxygen. Okay, so that's the difference. So this is not the same as a resonance structure. Okay, in resonance, all atoms remain connected to the same atoms, but number of bonds and lone pairs differs, okay? With isomers, the connections differ, okay? So that's thing number 1, okay? All right, so a type of isomers, okay, that you would get, okay, are when you still have, okay, the same number of bonds, the same types of bonds, but the positions are different, okay? So we've got the same number and type of bonds, but different positions in space, okay? So here we have 2 molecules, okay? They are both called 1,2-dichloroethene. Okay, this is a chlorine atom, the green. Okay. And you'll see we have a double bond between our 2 chlorine atoms. Okay. And remember that we cannot rotate around this bond. Okay, so important to remember. So, what's the difference between these 2 molecules? Yes, Rob. Where the chlorines are, right? So, and the difference is going to be, you know, are the chlorines kind of, chlorine is a pretty big atom compared to hydrogen, okay? Are the chlorines close to one another in space, like they are in the, these are labeled wrong, look at that. Well, actually, they're not labeled wrong, they're matched wrong with what they're underneath. So let me see if I can, I don't know if I can, you know what, I'm just gonna draw arrows. So this one right here is the trans when they're on opposite sides, okay? And this one right here is the cis. So I'll just change the color for that, okay? When they're on the same side, okay? And trans means opposite side. Okay? And so, you know, in this case, okay, we have a place where the chlorines are close to one another or whether they're far apart, okay? Now, to move between these 2 forms, okay, you have to have some type of chemical reaction take place that breaks the double bond, okay? So, conversion from cis to trans requires breaking the double bond, which means it needs a chemical reaction to occur, okay? Okay, so when you hear, you know, talking about dietary things, when you hear things like cis versus trans fats, okay, what they're referring to is a fat molecule, okay, has, so let's look at an example of a cis versus trans fat. Okay. So a fat molecule, things that are in fats or oils are what we call triglycerides. So you've got a glycerol with these three long hydrocarbon tails on it. Okay. So I've got something that has three things attached to it, and those things that are attached to it are these long carbon chains. So when I draw a carbon chain, when I draw something that looks like this, okay, what it really is, it's carbons attached to one another, okay, and they have, you know, hydrogens added so that each one is attached to four things, okay. So when I draw this, that's what you got, okay. And at the end, there's going to be three hydrogens, okay? When I draw something that has a double bond, okay, it'll be a line like that. So just this portion of the molecule, I'll have carbons attached with a double bond, okay? And so this carbon is only going to have one hydrogen attached to it, as is that, okay? And so cis versus trans fats, okay, I'll draw, so this will be a cis fat, okay, so it'll have a double bond here, okay, and if we zoom in on that double bond, okay, what's going to look like, okay, is I'm going to have my two carbons, and the hydrogens are going to be on the same side, okay. What that causes, yeah?
Just a quick question. Doesn't the double bond cause the entire chain to...
We're talking, that's what I'm about to say next, okay? So when we have a cis double bond, okay, the hydrogens are on the same side, and they bump up against one another, and it causes the chain to bend. Okay, so this is cis, hydrogens on same side of double bond, and then that long chain bends, and what that causes, okay, is that causes the molecules to not stack as well together, and that's how you get more fluid fats, okay, things that have a lower melting point, they're more liquid at room temperature. Okay, so chain bends, molecules don't stack together as well. I'm going to move this up. And what we get is we get a more liquid fat. Okay? Now, a trans fat, let me see if I can. So a trans fat is going to have the hydrogens on opposite sides, like the example with the dichloroethene right there. Okay? So what's going to happen is the hydrogens are on opposite sides, so they don't cause the chain to bend. So molecules can pack closer together, and you get a more solid fat. Okay, so, and what happens is trans fats typically don't occur much in nature, but when you do things like hydrogenate your oils to make like vegetable shortening or margarine, things like that, the process we use to do that creates a mixture of cis versus trans fats. Okay, so we get more trans fats produced that way. So a trans fat, okay, will have, again, it's still going to have like sort of three chains, but when we have the one chain that has a double bond, if we zoom in on it, okay, that double bond is going to have one hydrogen this way and one hydrogen that way, okay? And so what that results in, okay, so this is trans, and then the chain stays straight. Okay? And then that results in a more solid fat. And this slide got really busy really quickly. All right, so that's cis versus trans isomers, okay? And the thing that differs, okay, is can you just rotate about a bond where you get just a different conformation, or do you have to break a double bond to move the atoms around, in which case you'd have an isomer, okay? So let's look at these two. One of them is a conformation, and one of them is an isomer. So we still have the same atoms, same elements, the same bonds are connected, okay? But one of them is an isomer and one of them is a conformation. So can you figure out which one is the isomer? So the isomer, again, we're looking for what you're looking for is rotation around a double bond. So atoms wind up in on opposite sides of double bond, let's say. And for conformation, you're looking for just results from a rotation around a single bond. All right, so who's who? So the one on the top, are we changing the position of things with respect to the double bond, or are we rotating around a single bond? What was that? We're rotating around a single bond, right? So it's this bond right here, okay? Because we're changing, and it's hard to see, but so I'm going to draw like the wedge and dash. In this picture, it's that green atom is coming out towards you, and in this one, it's kind of going behind, right? So we've moved, we've rotated that group around. Okay, so that is different conformations. Which means this one is the different isomers. And in this case, right, we have the green atom on the bottom versus the green atom on the top. Okay, so to move this down to here, you have to break that bond and then reform it. Okay, break, rotate, reform, double bond. So those are the 3 steps that you need going between different isomers, okay? All right, so let's look at these guys, okay? Can these molecules have cis versus trans isomers? Okay, so first of all, which ones cannot? So you can tell right away that 2 of them can't. Because what do we need to look for when we're looking for cis versus trans isomers? We need a double bond, right? So these guys don't have double bonds. Okay, so so that brings us to the top. Okay. So now remember, cis versus trans, you have to have the same atoms connected. Okay, they're just going to be in space. Okay, so let's look at the molecule on the left for a minute. Okay, so I'm going to name my carbons. Okay, so this one's going to be carbon 1, and this is going to be carbon 2. Okay, so I could, okay, have an ethene that has two, dichloroethene, okay, that has a cis versus a trans isomer, okay, but in that case, they would have to be attached to different carbons, okay, those chlorines. Okay, so this, if I break this bond, rotate around it, and then reform it, is my molecule any different than what I started with? So let's break and rotate around. So here's, if I rotate around, I've got two chlorines, and they're still going to be attached to, and there's my hydrogens. So the molecule is going to be indistinguishable, right? So now if this were attached to carbon 2, okay, then I could have two different isomers. Yes, Sarana? Because, so the key is the same atoms have to stay attached, right? So if I try to move this here, okay, it's going to be attached to carbon 2, which is why I labeled them carbon 1 and carbon 2. So carbon 1, to be the same molecule, has to be attached to the two green atoms, okay? Whereas carbon 1 has to be attached to the two hydrogens. So yes, you can make a different version of this molecule, but a chemist would consider it a different thing, okay? So this is what we would call 1,1-dichloroethene. And so the previous one that we looked at is if I label my carbons carbon 1 and carbon 2. This is 1,2-dichloroethene, so one is attached to carbon 1, another one's attached to carbon 2. So they're different chemicals, they're different molecules, and they will behave differently chemically. So, yep, so good question. All right, so now let's look at this molecule right here. Okay, so I've got my two carbons. We'll name them carbon 1 and carbon 2. Okay, and again, they're pointing off in certain directions. So this one is coming out towards us. Okay, and this group back here is projecting behind. Okay, so what I could say is I want to move this group right here, okay? So I can rotate around this single bond right here, right? But all I'm doing is I'm spinning rotating around that bond would just spin the hydrogens, the carbon with the hydrogens. It's not going to move this whole entity so that it's pointing towards me, okay? To move it so that it's pointing towards me, okay, I would need to break and then rotate around that bond, okay? And then I could do that. I could get this whole group, okay, to then be facing outward, okay? So I can move where the hydrogens are just normally in space. So that would be a different conformation. But to make the isomer where this thing is coming towards me, or maybe flipping up so that it's above the plane of the double bond, I'd have to break that, move the entire thing, and reform it. All right, so that was a little bit longer than I wanted to be, but that's okay. All right, so we're going to move away from thinking about molecules in space, but we're still going to be thinking about molecules as particles and things. Okay? So the most important thing when we're doing chemical math is that you think of atoms and molecules as little objects. Okay? So key is think of all molecules as tiny objects, okay? And we're going to be counting objects, okay? And we're going to be figuring out, how to count tiny objects, okay? So this is the art of counting molecules, okay? We give a nice fancy name because we're chemists and we want to impress people with how smart we are, so we call it stoichiometry. That's not why we do it. We do it to communicate precisely, but so stoichiometry, okay, you've already grappled with in lab with the limiting reactants lab, okay? So the example we're going to start with today is not going to be a sandwich. It's going to be an ice cream sundae because that's a little more fun to eat sometimes. All right, so to make one, okay, to make this sundae, if we were working at Friendly's or somewhere, some big corporate ice cream chain that tells us exactly, how many ounces of ice cream you can give someone when they order a sundae, okay? They'll tell you, all right, we need 2 scoops of ice cream. You're allowed to put 50 milliliters of syrup. Let's say, this is the equivalent of, 1 pump from the Starbucks pump if you're having a caramel, mocha, high sugar latte, whatever. And it's going to have 1 cherry, okay? So every time I make one sundae, I need this many things of ice cream, this many cherries, and this volume of syrup, okay? If I were going to make 10 sundaes, I would need to multiply each of these things by 10, right? So, to make 10 sundaes, we'd need 2 scoops times 10, we'd need 20 scoops of ice cream. Times 10, we'd need 10 cherries. Times, 10, we need 500 milliliters of syrup, or if we're being fancy, we'd say 0.5 liters, okay? And that way, we would get 10 sundaes. So the concept is going to stay the same, okay? We are just going to use different units for the things, okay? When we use units of moles, we are counting like we count here. 2 scoops, 1 cherry, 1 50 ml aliquot of syrup, okay? When we're dealing with grams, we're not scooping 2 scoops, we're taking, say, 200 grams of ice cream, right? And if we want to turn that into scoops, we divide it up evenly. So we're going to be starting on the compound level. So in this case, our compound is the sundae, okay? And so if we call this, we'll call the ice cream I, we'll call the cherry C, and we'll call the syrup S, okay? And so our compound would be I2, 2 scoops, right? C1, and then let's say, a milliliter is a thing, so this would be S50, okay? Now, does ice cream weigh the same, does 1 scoop of ice cream weigh the same thing as a cherry? It doesn't, right? The maraschino cherry is much lighter, okay? And so each of these things, okay, is going to have its own weight, okay, its own mass, and the total mass of the sundae, okay, is going to be the combination of the masses of the individual components, okay? So I could do something like calculate the percent composition of cherries in my sundae, okay, right? I could say, let's say a cherry is going to weigh, let's say 5 grams, okay, 1 cherry. And let's say a scoop of ice cream is going to be 200 grams. And chocolate syrup, a little bit denser than water. Water is 1 gram per milliliter. So let's say chocolate syrup is 1.5 grams per milliliter times 50. What's that? 25 times 3 is 75. Okay, so let's say 50 mils of syrup. Oh, wait a minute. I was using 1 mil as my thing. So let's say 1 mil syrup is equal to 1.5 grams, okay? All right, so we're gonna start by talking about percent composition, okay? And so next class we'll do some chemical examples, but let's calculate the percent composition of ice cream in our ice cream sundae. So I'm gonna insert a page here, and I'm gonna take our formula and our things. I'm gonna copy it. I'm gonna paste it up here so we have, whoops, it didn't take the picture, but that's okay. We'll just move these things up here. All right, so this is our data. Okay, this is a sundae. All right, so I've got, how many scoops do I have? I've got 2, right? So each scoop weighs 200 grams times per scoop times 2 scoops. So that's going to be 400 grams of ice cream that my compound's going to have. Okay, so the first thing we're going to do is we're going to establish a formula weight. You've already done this. Okay, so we've got 400 grams from the ice cream. From the cherry, we've got 5 grams per cherry times 1 cherry. That gives us 5 grams of C, so plus 5 grams. And then we have our syrup, and we've got, 1.5 grams per milliliter times 50 milliliters, and that is going to give us 75 grams, okay? So that winds up being, 1 sundae weighs 480 grams, okay? So this is what a sundae weighs. I think I'm vastly underestimating the mass of ice cream, but that's okay. It'll be a teeny tiny sundae. All right, so let's figure out the percent of ice cream in a sundae. Okay, so all we're gonna do is we're going to take the mass from the ice cream. So this is the mass that the ice cream contributes to the sundae. And this is the total mass of the sundae. Okay, so the percent is going to be 400 grams divided by 480 grams times 100%. And I happen to have a calculator with me. And that comes out to be 83.3%. Okay, so your ice cream sundae is aptly named because it's mostly ice cream, right? So for practicing before next class, figure out what the mass percent of a cherry and the mass percent of the syrup is. And then we're going to start next class by calculating the mass of a chemical compound and the percent composition of each thing. And then we will then go in the other direction. So for this chapter, we're going to do calculations in one direction, then we're going to do them in the other direction. If what we can weigh is the mass of each thing, how can we figure out the formula, okay? So, all right, have a great Wednesday, everybody.